A Doppler Velocity Log (DVL) is a sonar-based navigation instrument that measures the velocity of a vehicle relative to the seafloor or water mass. It emits acoustic pulses and analyzes the frequency shift, Doppler effect, of the returning signals to calculate speed and direction. This provides accurate velocity data, crucial for underwater navigation and positioning. DVLs operate based on the Doppler effect. The device emits beams of sound at a known frequency. When these beams bounce off particles in the water or the seabed, the returning sound wave's frequency changes depending on the relative motion between the DVL and the reflecting surface. By measuring this frequency shift, the DVL precisely determines its velocity in multiple directions, typically fore aft and port starboard. DVLs use multiple acoustic beams, typically 3 or 4, that are angled downwards and outwards from the instrument. These beams create a measurement volume below the vehicle. Each beam measures the velocity of the water or bottom along its specific axis direction. The individual velocity components from each beam provide different perspectives of the vehicle's motion. These individual velocity measurements are then combined using mathematical algorithms. The algorithm calculates the vehicle's overall velocity vector, which includes both its speed and direction of movement. The number of beams and their specific configuration significantly affects the accuracy and reliability of the DVL measurements. Typically, 3 or 4 beams provide the optimal balance for precise velocity calculations. DVLs can operate in 2 primary modes: bottom tracking and water tracking. In bottom tracking mode, the DVL measures the vehicle's velocity relative to the seafloor. This provides highly accurate velocity information when the seabed is within the instrument's operational range. When the seabed is too deep for reliable bottom tracking, the DVL automatically switches to water tracking mode. In this mode, it measures velocity relative to the surrounding water mass instead of the seafloor. Bottom tracking is ideal for shallow water operations, providing precise navigation data for tasks like underwater surveying and pipeline inspection. Its trade-off is limited range in deep water. Water tracking enables operations in deeper ocean environments, but with reduced accuracy due to water currents and turbulence. DVL accuracy depends on several key factors. The quality of sonar transducers directly affects signal strength and clarity. Precise frequency measurements are crucial for accurate velocity calculations. Environmental conditions like water temperature and salinity influence sound speed, which impacts measurements. Several sources can introduce errors in DVL measurements. Sound speed variations occur when water conditions change, affecting how fast sound travels. Multipath interference happens when sound waves bounce off multiple surfaces before returning. Signal noise adds random disturbances that reduce measurement precision. Advanced DVL systems employ sophisticated signal processing techniques to reduce these errors. By filtering out noise and correcting for environmental variations, modern DVLs can achieve much higher accuracy in velocity measurements. Different tracking modes have varying error characteristics. Bottom tracking generally provides lower error rates because it uses the stable seabed as a reference point, making it ideal for precision navigation. Water tracking can have higher errors due to variable water currents and conditions. DVL data is typically integrated with other navigation sensors, such as inertial measurement units, compasses, and pressure sensors, to create a comprehensive navigation solution. The DVL provides accurate velocity updates to the IMU, which helps to reduce drift and improve long-term positioning accuracy. This sensor fusion approach is essential for autonomous underwater vehicles and remotely operated vehicles. Doppler velocity logs find applications across various underwater operations. They are essential for precise positioning, station keeping, and trajectory control in challenging marine environments. In real-world scenarios, DVLs play crucial roles in mission-critical operations. From scientific research to emergency response, DVL technology enables safe and effective underwater operations worldwide. Choosing the right Doppler velocity log depends on specific application requirements. Key factors include operating depth, accuracy needs, vehicle constraints, and budget. Different frequency options offer trade-offs between range and accuracy. High frequency provides better accuracy, but shorter range, while low frequency extends range at the cost of accuracy. It's important to evaluate DVL specifications carefully and select a model that matches your project's specific needs.